Hello physics students. So in the last few videos, you learned Faraday's law, which states that changing the magnetic flux through a coil creates a voltage. And this was very rich from a theoretical standpoint because magnetic flux depends on magnetic field and voltage depends on electric field. So what we learned was that changing the magnetic field creates an electric field. That's one of the consequences of Faraday's law. But also Faraday's law was very rich from a practical standpoint. As I mentioned in the last few videos, it allows humans to generate electricity. And so that, of course, leads to tremendous advances. Think about all the things we can do with electricity. We can wash clothes, we can use computers, we can watch entertainment. So very rich from a practical standpoint. Well, in this video, we're going to go further in terms of the practical aspects of Faraday's law. And we're going to see how a device that utilizes induction, which is called an inductor, how that affects an electrical circuit. Now, to build up to understanding what an inductor is, what I'm going to do is I'm going to come closer to the camera with this solenoid. And so we studied solenoids, and it's a coil that wraps around and around, and I can create a voltage in this solenoid, as we learned, by inducing or changing the magnetic flux through the coil. So suppose I magnetize this piece of iron. So it's got a north pole, and right now there's no voltage induced in the coil, but as I bring this north pole closer and closer to the end here, I am increasing the magnetic flux. There'll be a voltage that opposes the flux increase in this way to make a magnetic field the opposite way, and I could generate a current in this coil. Of course, the principle, as I mentioned, Faraday's law right here, the voltage produced here is equal to the negative time rate of change of the magnetic flux. But I don't need a bar magnet because there's another way I can make magnetic field in this solenoid. And that's by passing a current between these two posts so that the current spirals through, and we studied this in magnetism. I can create a magnetic field that comes out here or in there. So I make the magnetic field with the solenoid itself. Now here's the thing though. In order to induce a voltage, I need to change that magnetic field. And how do I change the magnetic field in a solenoid? I can change the current. So I've got current steady flowing. There's no voltage induced in this solenoid because we've got a steady magnetic flux, steady magnetic field. But if I try and increase the current, as I am increasing the current, the magnetic field increases. That will change the flux and that will make a voltage. So changing the current makes a voltage. Same thing when I try and decrease the current through the solenoid. Then what happens is whatever magnetic field I have, whatever magnetic flux I have, as I'm decreasing the current, that flux is decreasing, going away, because again, the magnetic field depends on the current in the solenoid. And so the decreasing flux will also induce a voltage in this solenoid. So any increase or decrease of current in this solenoid causes a voltage to be produced within the solenoid. That then is an inductance. So let me summarize on the board with some diagrams. So today we're studying inductors. By the way, we studied resistors. We had a symbol R for resistance, a symbol C for capacitors. Well, inductors, we use a capital L. And like capacitors, you could have a certain number of farads in a capacitor. Well, different inductors have different effects. They have more inductance than others. And inductance is measured in henries, which we can abbreviate with a capital H. A resistor in a circuit, we make a zigzag line. When you see a zigzag line, you know, oh, that's a resistor. Well, the way you diagram an inductor in a circuit is you make a spiral because essentially coils are, the spiral is an inductor. A solenoid, you could also call it an inductor. So let's take a look more specifically at what's happening when I try and increase the current in a coil. So before I try and increase the current, I have a steady current going like this. That creates a magnetic field going through the coil. I can figure that out by this right-hand rule. So I put my thumb in the direction of the current here like this, going down, and my forefingers point into the board. So that's the magnetic field caused by that current. Now, for whatever reason, I try and increase that current. Like maybe I have a volt power supply and I turn the power supply voltage up gradually and this gets bigger and bigger. That makes the magnetic field bigger and bigger. That's what I'm right here kind of in shorthand. I increases, B increases. What happens, we learned from Faraday's law and Lenz's law, that then there will be an induced magnetic field. It's a law of nature that tries to oppose this increasing magnetic field. So more and more B this way, we get B out this way. That then makes a voltage. If we put our four fingers in the direction of that induced B, you see you have a voltage that's now, by the right-hand rule, against the current. So as you're trying to fight and add more current in, you've got a voltage that's fighting you. So the device fights the increasing current. It doesn't mean that you can't increase the current. It's just not as easy as if that device wasn't there. The current kind of fights, you got to get it to go up more gradually. Same thing happens when you're trying to decrease the current, or a similar effect. So again, we got current going like this, through this wire loop, through the right-hand rule. There's the magnetic field caused by that current. And then as I'm trying to decrease the current, what's going to happen is there will be induction. There will be an induced magnetic field that tries to fight the decrease. It fights the change. So how do you fight the decrease of this? You make more be induced to try and keep the magnetic field going. What then does that do in terms of voltage? I use this right-hand rule. I put my four fingers in the direction of B induced, and I see there's a voltage induced in this particular direction, in the same direction as the current. So decreasing the current, I try and make this go to zero, but the inductor kind of tries to keep it going and fights me in terms of decreasing. So I goes down, B induced, and M induced are now in the same direction. Oops. That should, as the current and the magnetic field. See, same direction and then same direction. So the device fights the decreasing of the current. So let me create a pause and give you a chance to copy these concepts down. Okay, so as I said, you can still increase or decrease the current in here. It's just that it's fighting you. The analogy that people use is like a mechanics analogy. You got a car going by you 10 miles an hour. And it's just going to keep going because that's what cars do, keep going, stay in motion. Now let's suppose I want to increase the speed of the car. I push on that car and it doesn't take off like a piece of paper, fly away real fast. I can speed up the car, but it kind of fight the inertia, the mass of the car sort of fights me, and I could get it from 10 miles an hour to 20, but only after a considerable amount of time. Same thing here. I could get this from 1 amp to 2 amps. It's just that it's fighting me, and I gradually fight it and push it to get it to 2 amps from 1 amp. And the same thing with a car, 10 miles an hour, steady, steady. Now try and stop it. So you push backwards on that car. And it's not like a piece of paper, and it stops almost instantaneously, more or less. It's a car, so I got to push it, and it takes a long time to get it down to zero. Same thing here. I want to get this 1 amp to 0 amps, so I try and decrease the current, but the inductor's fighting me and trying to keep it at 1 amp, so it goes gradually from 1 amp to 0. So an inductor in circuits is like inertia or mass in mechanical systems. It's like an inertia for current. All right, I'm going to continue on, fill up the boards with all just concepts like this to see. We're going to work through the practical consequences so you could really feel and understand intuitively what an inductor does in a circuit. So that's kind of the magnetic effects. Now let's take a look at some basic circuits and see how it's going to affect the current as a function of time. So the effects shown graphically. Case 1A is current begins at 0. You have this switch open. And then at time 1, I flip this switch down. So it's 0, 0, 0. And then at some maybe 3 seconds into my experiment, I flip that down. Now, without an inductor or without an inductance in the circuit, as soon as this switch taps down here, we've got Ohm's law, I equals V over R, and the current shoots up instantaneously and becomes whatever amperage V over R is. So the change is nearly instantaneous. But if you put an inductor here and you try the same thing with the current beginning at 0 and you flip the switch down, what happens is now as the current starts going this way, we're increasing the current. So we go from like 0.01 amps to 0.02 to 0.03. The increase, the derivative of the current is going in the same direction as the current. So the voltage induced will oppose that increase. So the inductor makes an nth of the inductor against the current. And that doesn't mean the current can't increase. It just means it has to increase gradually. So there's the graph. And you could kind of see where we're going to be going in this topic. Differential equations, 1 minus exponential function here. And so that's coming in a future video. So go ahead and copy these notes down just to, sort of get the more concepts into your notebook. All right, let's take a look at case 2A. What happens here now? We have this kind of interesting circuit here. We have the switch, maybe I should say position A and position B. And so it's in position A, and we've got the current in this circuit would just be from Ohm's law, V over R, whatever that I0 is, and it's steady. And then at a particular time 1, I quickly flip that switch down to position B. The battery's gone, and all I have is a resistor and some wire, no voltage source. So from Ohm's law with 0 voltage over resistance, 0 current. The current instantaneously drops to 0. No lagging effect at all without an inductor. But now let's do the same thing, but let's stick an inductor over here, which has that inertia effect. So we're in position 1, A up here, and we wait. And the current gradually builds up, and then we wait long enough so it's like whatever amperage, maybe it's like 3 amps or something up in position A. And now we begin our timer, and it's steady 3 amps because the inductor's got current going through it. And then I instantaneously flip the switch to B at time 1. Now the old way without the inductor drops instantaneously, but what happens is the current in the inductor is to the left. And by decreasing the current, the derivative is in the opposite direction, because the current goes from, say, as I said, 3 amps to 2 amps to 1 amp to 0 amps. So the derivative is that way. And again, the inductor opposes the decrease. So it makes a voltage opposite of the derivative, opposing the change. In other words, in the same direction of the current, it keeps the current going for a little bit. And it lets the current drop, or makes the current drop at exponential decay instead of instantaneous drop. So let me pause, create a pause so you could copy those notes down. All right, so there are concepts. Inductor fights change, some circuits, how it makes gradual changes instead of instantaneous changes. Now we need to move on to some quantitative analysis with numbers. How do we do calculations with this? So let me make some room. Okay. How can you calculate the inductance of something? How many henries a particular device is? So L, you could It's basically this, N now let me write out what this is. N is the number of coils. Oh, maybe I'll do 2 lines. So that's what the formula is. It's the total number of coils. What I would have to do is, be pretty tedious for this, count up how many times this wire wraps around this solenoid. That would be N. Calculate the flux through the solenoid through one of the coils. So that'd be like the total flux through all the coils in the solenoid or the inductor, and divide by the current. It's basically like, you could think of it as, how efficient is this at creating magnetic flux? The more flux it makes per current, the more it's going to be stubborn, the more inductance it'll have. That's what L is. And then the big idea here, which is just Faraday's law worked out or reworked, is that the inductor makes voltage whenever the current changes by this magnitude. The bigger the inductance for a given voltage, the smaller this. So this is a voltage battery you apply over here across the inductor. The bigger this is, the smaller this is. So the change is much more gradual. The smaller this is, the larger this could be. So the current could jump up faster if this is smaller for a given battery voltage that's applied to the circuit. Now, just to give you, let me create a pause so you could copy this down. All right, so in another video that I'm going to create, just to separate this in length a little bit, we're going to actually calculate or figure out how you can calculate the inductance of a solenoid. But just to give you an idea, I had a meter, and I won't do it because, I don't want to make it too tedious, but this meter can measure the inductance of the device. I hooked it to this solenoid, and I got about 0.007 henries for this solenoid, just to give you an idea. This is a commercially manufactured inductor, which you look is much smaller than this. And yet this is, instead of 0.007, this is 0.1 Henry. So this little thing has about 15 times the inductance of this, because like with capacitors, when the engineers, they can make the inductance much higher with materials and geometries. So just to give you some ideas of, if you calculated this, what you would get for some devices for inductance. All right, let me do an example calculation. So we've got a 0.1 Henry inductor, basically that little device here that I mentioned. So this inductor, and we're going to change the current by this expression, and we want to find the voltage that this inductor produces, either keeping the current going or preventing it from rising too rapidly at 2-second mark, given that a current. So what we have to do is we will start with our expression. I'll stay with symbols in the beginning, and then I'll plug in all the numbers only at the end. So I put the current expression here. Now, if we were in class, I would say, okay, everyone, write down what this derivative is, but I'll do it for you. So it's a simple power derivative. We could move this 3 to the front and get 12t, and then subtract 1 from the exponent. You get squared minus 2 times 3, or 6t, and then subtract 1 from the exponent, t to the 1, which is not even necessary, the little 1 power. Continuing on, so I could maybe distribute the minus sign and get that the mth is, should I factor out a 6? Why not? 6L t minus 2t squared. Let me just look that over to make sure I didn't make any mistakes. Let's see, so you got this. Yeah, I think that's good. Now I can plug in my data. So let me go ahead and 6 times 0.1 Henry, 2 seconds minus 2, yeah, so if you plug in 2 seconds here, you get a positive current. So the voltage is against that, which means we're trying to, at that moment, the current is increasing through that inductor. And so there's a voltage sort of holding it back, like the inertia of the inductor, inertial effect. All right, let me create a pause to allow you to copy these notes down. Okay, so that's it for this video. Like I said, I'm going to make another video just to break things up a little bit for calculating the inductance of this using this formula. But again, what happens is whenever you try and increase or decrease the current, that changes the magnetic field caused by the loop itself within the loop, which induces a voltage that either opposes the increase or opposes the decrease in the current. It's like an inertial effect. And the basic calculations, the formulas we learn is how to calculate the inductance, the henries of any particular coil of wires given by this formula. And then once you know the inductance and the current, you could calculate the voltage that's generated in that inductor because of the change in current. So that's today, inductors and their effects on circuits. I'll see you in the next physics video.